All right, here's the plan for today. We are going to start with something relevant for the next electronic assignment, and that is to simulate sampling from a normal distribution using a spreadsheet. I said the last stuff we did was the hardest. This is easier, but it's still a challenge. You're still going to want to pay attention, at least if you don't want to have to watch the video after class, to what we do here, to know what to do on the assignment. We introduced briefly the power of the test in type 1 and type 2 errors. Last time we'll go into more depth. And these ideas are on today's quiz, so you want to pay attention for that. In lecture B, we're going to start the next chapter about being more realistic with things. So far we've been assuming we know the population standard deviation. But if you don't know the population mean, why would you know the population standard deviation? Okay? In real life, people don't typically, almost always, they don't know the population parameter values. So you need to make adjustments for not knowing that population standard deviation. And we use something called a t-distribution instead of the normal distribution. Although t-distributions are still symmetric like normal distributions are. Alright, so let's start with the sampling. So this will be your electronic assignment. So here we have a spreadsheet that is labeled, the mean and standard deviation of the normal distribution being sampled from. Okay, we're sampling from a normal distribution. That's the title of the spreadsheet here. Here are the mean and standard deviation. Okay, I just made these numbers up. I'm pretending I've got a population with a mean mu of 20 and a standard deviation sigma of 10. I'm pretending that I know those things. And this is going to simulate sampling from this distribution. What's the purpose? The purpose here is ultimately going to illustrate the idea of a confidence interval, actually. We're going to be computing confidence intervals over and over and over again for, in fact, 25 different samples of size 36. I've got the observation number here that goes down to 36. 36, that's the last observation number. In other words, my sample sizes are going to be 36. I've got spaces for the sampled values that I'm going to sample from this distribution. I'm going to sample from the population. These are going to then be samples of size 36, and they're going to do 25 samples of size 36. We don't have to use a bunch of ifs here. That's what makes this a little simpler, okay? Though you do need to pay attention to what you do. We end up using NORMINV. Now I did use this before, back about a month ago perhaps, maybe even longer, 5 weeks ago. We used NORMINV, or right around lecture 6 or 7 I think. What does NORMINV do? It's called the normal inverse. Looking at the syntax here, it requires 3 inputs. The first input it calls x, the second input it calls the mean, and the third input it calls the standard deviation. The mean and the standard deviation come from these two numbers, cells C2 and C3. What is x? X is going to be a number between 0 and 1. In fact, I'm going to use rand to pick a random number between 0 and 1. Essentially, it represents an area under the normal curve to the left of whatever number you are after here. So to draw a normal curve, let's go ahead and use this mean of 20 and the given standard deviation that I have of 10. When I plug in a value for x, it's really going to represent an area to the left of some number under a normal curve like this. And NORMINV is going to give you the value of this number that I don't want to label with an x. I'll just label that number question mark. What number has an area to the left equal to x? That's what NORMINV does, okay? You plug in areas, you get a number on the axis. I'll say it again. That's going to be confusing. Here is a picture of the distribution that I'm sampling from. Mean of 20, standard deviation of 10. When I plug in a number for x, that represents an area. For example, if you plug in 0.75, and plug in the mean in cell B2 and the standard deviation in cell, C2, and the standard deviation in cell C3, that is going to give us an x value. In fact, you can see it there, 26.7, right around there, such that 75% of the area is to the left of it. If I plugged in 0.9 instead of 0.75, I'd get a bigger number because you can see what it is. 32.8 is over here. That's a number so that the area under this curve to the left of 32.8 is 0.9. However, I'm not going to continue plugging in 0.75, 0.9. Instead, I'm going to plug in rand. Remember just what a plain rand does? It generates random numbers that are not whole numbers between 0 and 1. Random decimals, you could call them. Random areas in this picture. So I'm going to plug in rand into that. I'm still going to use the same mean in cell C2 and the same standard deviation in cell C3. But now because the first input is rand, it's going to be a random number between 0 and 1. That's going to mean the output is a random number as well. In this case, it's saying the output's going to be 17.9, but it'll probably change when I enter it. And it will simulate sampling from this distribution. That's the point. By combining the NORMINV and the rand in this way, essentially giving it a random area, I get a random question mark that follows this distribution. The values will typically be close to 20. Well, sometimes they could be far away. That standard deviation is fairly big. Copy and paste those, you get a bunch of numbers that should average out close to 20. That's the point. If you now take the mean of these numbers, that's really like an x bar. Do equals average. Equals average, starting in cell D6, going down. Not what I'm doing here. D6 through D41. That'll compute the mean of those numbers. That will typically be pretty close to 20. That's an x bar. Okay? Don't feel you have to completely understand the NORMINV thing right now. Okay, we will use this more. I did describe what it was. Based on an area for x, it's giving you the value of the question mark. And by plugging in rand in place of x to get a random number between 0 and 1, this will then simulate sampling from a distribution like this that's got a mean of 20 and a standard deviation of 10, and is a normal distribution, in fact. You get an x bar value. We want to calculate now a 90% confidence interval as well. Based on that x bar value, remember, so far our confidence intervals, the formulas have been of this form. Today we're going to change that. What do I have over here? I've got the standard deviation of the sampling distribution of x bar. How did I find that? Look at this formula. It's equals C3 divided by the square root of 36. That's this quantity right there. The sigma was 10, the n was 36. This number right here, 1.6 repeating, is the standard deviation of the sampling distribution of x bar. It's the number that goes there. I'm after a 90% confidence interval, so I then take that number right there and multiply it by, based on table D, I multiply it by 1.645. If you look back in table D, the very bottom of the table, and you want 90% confidence, at the bottom of the table, the z star is 1.645. You get a margin of error of 2.7417 approximately. Now I can use that. I can take the mean that I calculated, subtract that margin of error, which is in cell B47, use dollar signs. That'll be the lower end point of a 90% confidence interval. Then add, take the sample mean, x bar plus the margin of error in cell B47. That'll be the upper end point of a 90% confidence interval. Then I'm wondering, does that capture mu? I can use if here, but it's not going to be a mostly used if. And it seems, okay, this is going to be a little bit complicated. It seems like when I tried this before class, it would make sense to do this. Is 20 between those two numbers, but it didn't work when I did that. So I had to do something else. I have to use another command called AND. Is that less than 20? And is 20 less than this is what I had to do. I'm wondering, does this capture mu? Mu is 20. The AND, what that does is it tests to see if both of these conditions are true. Is the lower end point less than 20, and is the upper end point greater than 20? If that's true, then I'm going to say it's captured mu. And I'm going to say yes. If it's not true, I'm going to say no, it's not captured mu. So I guess this is still fairly complicated. It's not as complicated as last time, but so I'm not using multiple ifs, but I am using an if and an and in kind of a confusing way. Again, what does this do? It tests, is this number less than 20? And is this number bigger than 20? If that's true, that means 20 is between these two numbers. It's in the interval and you return a yes. If it's not, then you return a no. That captured mu. Now copy and paste all this. We're doing this 25 times. Copy and paste it all the way to the right. I've automatically given enough columns to make this 25 times. Once again, what does this represent? This represents 25 samples of size 36. Most of the intervals contain mu. Yes, 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 yes. Some of them don't. No, no, no. These three don't. What percentage do contain mu? It should be close to 90% over the long run. Is that the case here? Count how many yeses there are and what percentage they are. Out of 25, there are 25 samples here of size 36. Count those if they equal a yes, and divide that by 25. It should be relatively close to 90%. 88% with this one. That was harder than I was expecting. Sorry if I wasn't expecting that to be as hard to describe as it was. I guess I would say that is almost as hard as the previous one. Big picture again. I do want you to understand the point here. The point is to illustrate the idea of a confidence interval. We're sampling from a normal distribution with a mean of 20 and a standard deviation of 10. I'm pretending those are population parameters that I'm pretending that I know. Each of these columns represents a sample of size 36. I'm using the NORMINV and the RAND to create these values that I'm pretending are sample values from that distribution. From those numbers, I can calculate their averages. Those are like X bar values. I can calculate sigma over square root of n. Over there, that's the standard deviation of the sampling distribution. I can calculate z star times that for a 90% confidence interval. Again, that's 1.645 is the value of z star. Then I can use this formula. I can do plus or minus to calculate the lower and upper endpoints of the corresponding interval. Notice you get different answers for different samples. That's a real fundamental thing in this class to realize. Then the question is, what percentage of these contain the true value of mu? We used if and that was the hardest part here, to decide if it captured mu, and to return a yes if it did, and to return a no if it doesn't. And then finally we used COUNTIF and divide by 25 to calculate the percentage of those samples that contain mu. And again, the answer should be close to 90%. If you redo the sampling, you'll get a different answer. That time we got 92%. but generally speaking, it should be close to 90%. That's the meaning of the 90% confidence interval. That's the meaning of the 90% in repeated sampling. About 90% of the intervals contain mu. Sometimes I'm too ambitious, but now it's recorded, okay? And I think once we've done this the first time, it'll be easier in future times. For the rest of lecture A, we want to focus on calculating something called the power of a test, the probability of a type 2 error of a test, and know ahead of time what the probability of a type 1 error is. I briefly introduced those ideas, so now in the context of an example, I'm going to describe those ideas in more detail. Okay, I'm trying to put this in an applied context. Thinking about a business example, suppose you've got an advertising campaign, you're trying to generate new sales based on a new advertising campaign. Based on past data, the old advertising campaign generated sales at a rate of $50 per customer each month. So for everybody who ordered, they ordered on average $50 worth of merchandise. Not saying how many people actually ordered, that's sort of a separate issue. And the standard deviation of how much they spend is 40 per customer. Now you're planning a new advertising campaign and you want to know, does it increase your sales per customer? It's only going to be worth it. You know, new advertising campaigns cost money. It's only going to be worth it if you can increase your sales to $60 per customer each month. So how do you decide whether you do it? You take a random sample of customers and see if it increases their mean to 60 or more. Here's the random sample of size 64. See how much they spend. Based on how much they spend, it helps you make a decision. Should I use the new advertising campaign or not? X bar, the sample mean for those 64 customers, could indeed be bigger than 50. Could be bigger than 60. It's a question of how much bigger than 50 to decide whether you should reject the null hypothesis that the new mean for the new advertising campaign really is bigger than 50. We're going to use a 10% level of significance. We're not actually going to do the test here. We're going to first define the parameter we're testing and set up null and alternative hypotheses. And then we're going to calculate some probabilities that are new kinds of probabilities to calculate. These are planning kinds of probabilities, calculations you do before you actually do the sampling. The p-value, by contrast, of a test is a probability you calculate after you do the sampling. That helps you decide whether to reject the null hypothesis or not. So let's take it step by step. First, define the parameter you are testing and set up null and alternative hypotheses. Define the parameter and set up hypotheses. That's the first thing we're doing here. Mu is going to be a population mean. What population? Well, it would be the mean sales per customer if you gave the new advertising campaign to everybody, all your customers. All customers from the past, say, and then maybe all customers from the future. The mean sales per customer each month for all customers. That's the thing that you hope is bigger than $60. So justify creating and using this new advertising campaign. That's a definition of the parameter. What about the test? You're hoping certainly that mu is bigger than 50. You're hoping the alternative hypothesis is true, at least if you really want to do this new advertising campaign. Really, you hope for more than that. You hope that mu is actually bigger than 60. But let's initially set this up as a hypothesis about whether mu has changed from the past or not. Remember, the null value is often the statement of no change, no difference. The past sales generated, the past advertising campaign generated sales at a rate of $50 per customer each month. So the null hypothesis would be there's no change. Mu is 50, the same as it used to be for the old advertising campaign. I should add here, with the definition of mu, this would be under the new advertising campaign. Because that's what we want to know about. You haven't shown the new advertisements to the customers yet. Maybe somebody has created some sort of pre-advertisement instead of a full advertisement, so you're not spending money on a full advertisement campaign. That's what you want to know about, so you should focus on the new advertising campaign. So that's a definition of the hypotheses, or the parameter. Here are the hypotheses. Now, the second thing we're going to do is calculate these probabilities. Find, part A, the probability of a type 2 error, type 1 error. B, the probability of type 2 error. And C, something called the power of the test. Three things to do here. I did briefly mention what type 1 and type 2 errors were last time. Talked about it in the context of a courtroom. If you pretend you're the prosecuting attorney, the null hypothesis is the assumption of innocence. The alternative hypothesis is that they're guilty. As a prosecuting attorney, you, maybe by taking the case, maybe not, are convinced that they are probably guilty, and then it's just your task to prove that beyond a reasonable doubt. A type 1 error is when you're successful when you shouldn't have been. You convince the jury that they're guilty when really they're not. You reject the null hypothesis, the jury rejects the null hypothesis, when in fact the null hypothesis is true. A type 2 error is the opposite kind. You failed to do your job. You failed to convict when you should have convicted. You should have convinced the jury because that defendant is actually guilty. That would be a type 2 error. So a type 1 error is when you reject the null, reject the null when the null is true. And a type 2 error is when you fail to reject the null when it should have been rejected, the null is false. Turns out you can calculate the probabilities of these, and the first one is very easy. There's really no work to do. You get to decide what the probability of the type 1 error is, and you decide by stating what your level of significance is, what your alpha is. That's the answer. That's the probability of a type 1 error. When you decide on the level of significance, when you decide how strong does the evidence need to be against the null hypothesis before we reject it, you are deciding on the probability of a type 1 error ahead of time. Remember, low alphas correspond to needing strong evidence before you're going to reject. So it should make intuitive sense that if alpha is really low, like 1% or lower, you're going to need real strong evidence before you're going to reject. You're not going to be likely to make a type 1 error. You're not going to be likely to reject the null hypothesis when it's true. In fact, yes, setting alpha does define, essentially, your probability of accidentally rejecting the null when you should not. You should not have. It's your probability that your p-value ends up being less than the alpha if the null hypothesis is true. If you assume the null is true, you have that chance of getting a p-value less than alpha when you decide what alpha is. So that's easy. Probability of a type 1 error is easy. You decide, or the book tells you, or I tell you on a quiz or test. These other probabilities of a type 2 error and the power of a test, those are harder. In addition to being harder conceptually, you also have to decide to assume a certain alternative value of the parameter. In this case, we're going to decide that $60 is the truth about the parameter. That is an alternative value. It satisfies the alternative hypothesis. Why did we pick 60? Because that is the minimum we'd like the sales to increase to in order for us to truly feel confident that it's good to go ahead and spend the money on this new advertising campaign, that it's worth the money and time invested. So I'd like to be able to reject the null hypothesis correctly when the truth about mu is that it equals 60. So I'd like to calculate the power of the test. How likely am I to be able to do that? And on the flip side, I'd like to be able to calculate the probability of a type 2 error. In fact, these two probabilities, the probability of a type 2 error and the probability of the power, which is the probability of correctly rejecting the null when it's false, those have to add up to 1. They're complementary events. If the null is false, and this alternative is true, you're either going to reject the null or you're not. If you do reject the null correctly, then you're in the situation where that probability related to the power happened. And if you incorrectly fail to reject the null, then you're in the situation where you made a type 2 error. So those two probabilities have to add up to 1. So they are harder to calculate. Well, let's go ahead and calculate them. What's the probability of a type 2 error, first of all, given that mu is 60 instead of 50? I can't do the calculation right away. Okay? I've got to do some other calculations first before I can do this. Before I can calculate this probability, I have to decide what the rejection region is for this right-tailed test. It is a right-tailed test, by the way. I erased the alternative hypothesis, so it was a greater than sign. I have to decide what the rejection region is first. That's the first step before you can actually calculate this. How do you do that? Well, you base it off the value of alpha. Alpha is 10%. We're doing a right-tailed test. What's the critical z value? First of all, z subcritical. That makes this area 10%. This area equal to alpha, which is 0.10. We did this last time, this calculation. You need to use table A. How do you use table A? This is a right-tailed test. So you're looking for a number in table A where the area to the left of it is 1 minus 0.1 is 0.9. Closest one to 0.9 is right there. 0.8997 is what that number is. That corresponds to z equals 1.28. So the critical value for rejection of a right-tailed test when alpha is 0.1 is 1.28. You need to convert that now to a critical region for rejection for the original distribution of numbers, based on the fact that if the null hypothesis is true, it's at 50 instead of 60, we can figure out what x critical value will lead to rejection by using this equation. X critical will equal mu plus sigma times z critical. In effect, I'm unstandardizing z based on the assumption that the null is true, which is what you assume when you do the test. So mu is 50. Sigma, what do we assume for sigma in this problem? Sigma was 40, up there at the top. And the critical value z was 1.28. Now use your calculator. to calculate that critical value for x, 50 plus 40 times 1.28. 101.2, that's the critical value for x. That's going to lead to rejection in this situation. Or you know what? I made a mistake. I'm sorry. I got to divide this by the square root of the sample size. I was thinking that number's too big. What was the sample size? The sample size was 64. Square root of 64 is 8. 40 divided by 8 is 5. That should be a 5 there instead of a 40. $50 plus 5 times 1.28. 56.4, that's better. So the critical value of x that's going to lead to rejection for this right-tailed test is 56.4. If x bar is bigger than 56.4, then we're going to reject. Okay, now we can go back to the probability of a type 2 error. What again is a probability? What is a type 2 error? It's when you fail to reject the null when you should have. You're assuming this alternative value is true. What does it mean to fail to reject the null? It means you're not in the critical region. X bar is not to the left of 56.4, it's to the right of it. Or it's not to the right of it, it's to the left of it. So this is the probability that X bar is less than 56.4. Again, given that mu is 60. Now standardize. Convert to z. Using the assumed value of mu at 60 here in this calculation. I'm not going to bother writing this as a conditional probability anymore. I'm just going to subtract 60 here and divide by 40 over square root of 64, which is, again, the same as dividing by 5. This is the probability that z is less than negative 3.6 over 5, which is the probability that z is less than negative 0.72. From table A, that probability is right here. Negative 0.72 is what I'm looking at. That number is 0.2358. It's hard for me to see even when I'm this close. I know it's hard for you guys. You should have your book open. 0.2358 is that probability. The power of the test is 1 minus that number. Remember, the power is the probability of correctly rejecting the null when the alternative is true. It is the opposite event of failing